Nasath, how are you? Amazing Amanda, how are you? Random guy, how are you? Very nice. Love it. So, in going from the Newtonian to the relativistic form of understanding gravitation, because we can understand gravitation in a Newtonian way, that stuff that I was talking about with the GMM over R squared and, you know, all of that, where the inertial mass turns out to be equal to the gravitational mass, all of that is fairly simple. It's the Newtonian mechanics way of doing things. But then remember, Einstein was inspired to give us a more correct theory of gravitation with his general theory of relativity, where we consider basically massive objects to be able to bend space and time, and gravitation is more of a curvature of space and time. And so there's more curvature near more massive bodies like black hole and neutron stars, and less curvature near in the intergalactic medium or in intergalactic voids. But then we talked about how when you go more large scale, at a scale of around 100 megaparsecs, you see that these everything is more homogeneous and isotropic, and the inhomogeneities are really seen at a smaller scale. Oh, Suji's taking care of Fuji and herself. So now we will talk about the cosmological constant, which is often denoted by the Greek letter lambda. It's a capital lambda. The Greek capital lambda is a symbol for the famous, or perhaps infamous, cosmological constant. This cosmological constant we have also mentioned several times on the channel. Well, it has a checkered history. It goes back to the year 1917, when Einstein published his first paper on the cosmological implications of general relativity. Ooh, can we get 20 likes? In a formal mathematical sense, cosmological constant is a constant of integration resulting from Einstein's field equations, from solving those field equations, which are a set of differential equations. In addition, however, the cosmological component can be given a physical meaning. A close look at the Friedmann equation shows that adding this lambda term is equivalent to adding a new component to the universe that has a constant energy density. Thus, any component of the universe whose energy density is constant with time will play the part of a cosmological constant. One such component is the vacuum energy. In quantum physics, a vacuum is not a sterile void. The Heisenberg uncertainty principle allows particle-antiparticle pairs to spontaneously appear and then annihilate in an otherwise empty space. Just as there is an energy density U associated with real particles, there is an energy density U vac associated with the virtual particles and antiparticles. The vacuum energy density U vac is a small-scale quantum effect that is unaffected by the large-scale expansion of the universe, and hence U vac remains constant as the universe expands. Unfortunately, quantum field theory cannot tell us the expected numerical value of U vac. So then we can rewrite Feynman equation in terms of the energy density of the universe and whatnot. We also include energy density U lambda. And then radiation density UR is the energy density contributed by relativistic particles, such as photons, and the matter density. So